looking at this graph here and to ask and just have me ask you, what does the red line represent? Okay. So I think on your printout it's a little more clear, but we've got a point here and we've got a red line here. I think the function is in black pen. What does that red line represent? Awesome! Represents the tangent line. So if that red line represents the tangent line, and here is the line that expresses the equation, then what is that equation called? What is that equation called? Just put it together. It's the equation for, it's the equation for the derivative or for the tangent line. Okay. But it's the equation for the tangent line. And what point is that equation going through? Relative to the function. Yeah, 0.01. So it's the equation for the tangent line at x equals 0, right? You said 0.01. And when we talk about this fancy term called linearizing or linearization, it's exactly just finding this, which you've been doing for a really long time. You've been finding equations for tangent lines for a while now. We're just giving it a fancy name. Okay? That's all that's happening here. It is also the first step in doing something called Newton's method. Okay? Both of these, linearization and Newton's method, are what we call approximations. What does it mean to approximate something?
Like close, reasonable.
Yeah. You have a value that's a guess. It's close, it's reasonable. It's all those things. Okay? And so we use linearization and we use Newton's method to get approximations, to get an answer that's close and reasonable. Okay? How are we doing so far? Okay, in order to talk about linearization, we need to kind of review some concepts. For instance, if we look at that line and wanted to calculate the slope, give me the slope equation to do that. Go back all the way back to algebra. What's your slope equation? Yeah, and we've seen it written like this, I think probably more often than not. Right? Whether the two comes first and the one comes second or vice versa, it's not really a big deal, right? Just be consistent. And so that equals the slope, and slope is typically the variable m, right? When we look at these terms, or when we look at these variables, which part of this equation is kind of closely related to calculus? The concept of what? The concept of finding points, the concept of finding a slope. What's kind of closely related to calculus?
Physics.
of these things, finding points, finding slope. Which one has ties to calculus?
Slope.
Slope, because we know in calculus slope is what? Is what? How do you calculate slope? What do you have to do?
Slope equation.
How do you calculate the slope of the tangent line? We have to find what? The derivative, exactly. Okay, it was kind of a stretch. But really what we can say, you know, if we want to put we need to kind of put a calculus spin on this, we can really say that this slope is really the derivative. I'm going to call the derivative f prime of x. So we really could kind of say that. Right, as long as that slope is the slope of a tangent line. Okay. Does anybody remember point slope form? Because from this we can get point slope form. What does point slope form look like?
They're like y minus y1 equals m times x minus x1.
Okay, so there's our slope point form. So looking at our expression for our slope equation above, we can say that if we rearrange this, our point slope form might look like
y2 minus y1 equals f prime x times x2 minus x1.
right. Okay. And so this is really the linearization process. Is we're going to take the point slope form because it's the most convenient. Can we get that into slope intercept form with a little more algebra? Sure. It's not really necessary unless like WebAssign asks you to do it. But really we're just going to focus on using the point slope form. Okay? So what does it mean to linearize? Well, if I'm going to linearize, I better end up with that line. And so if we start with this function here, and we want to linearize this function, what we're saying is we're going to come up with literally an equation for a tangent line at a particular point. Okay? We're literally going to write the equation for the tangent line through that point A. So if we want to write the equation for that tangent line, we have a point and we have the slope. And so we can write the slope point form of the equation of that line. Does that make sense?
For the y2 and the x2 then, is that just left as y and x?
Yeah, so if we start back from our last page, and in fact I'll start one step before we change the page and put the slope, the m back in for slope. So we're going to leave the y2 and the x2 because we need the y and x in our equation, and we'll just call those y and x. And then the y1 is what, according to the notation I have?
Oh no, f at a.
Is the function f at a. And the slope is what, according to the notation?
Prime.
The derivative at, the value of the derivative at x equals a. And x1 is what?
A.
And really, I think the bigger challenge today is becoming comfortable with the notation. I think we're probably comfortable with calculating slope y2 minus y1 over x2 minus x1. I think we're probably pretty comfortable even with point slope forms of equations. It's just that the notation might look a little weird. Okay? So that is the definition then. If you look at this and you look at this, what did they do? That's, how did they rearrange this to get this expression here?
They added the f of a.
Yeah, they just did this. Let's solve for y. Okay, so they said, let's just solve for y. So I have this value of my function at point A plus the derivative times x minus a. And that is called the linearization. Again, linearization is just writing the equation for the tangent line at a particular point. We've been doing that for quite some time. But the one thing that we haven't done that we're going to do with this is we're going to use this to approximate the value of a function. Okay? So if we look at the function and the linearization, the tangent line here, can you see that there is a gap between the two over here to the left of A? So there's a gap between the two in this area, and that gap goes all the way up to that point. What happens to that gap as we approach A?
Gets smaller.
Smaller and smaller. And then at A, is there a gap? Is there a gap at A?
No.
There isn't. The gap actually literally disappears. And then on the other side, that gap starts up again, and as we progress away from A, what happens to this gap?
Gets bigger.
Gets bigger and bigger. So let's go back to what we said an approximation was. It was a guess. It was a good guess. It was a reasonable guess. It got you close to the value. So if I would use this line to approximate my function, so if I use the red line to approximate the green value, where can I use that approximation relative to the point A?
Close to.
Does that make sense? Why can I only use this line to approximate the green values only when we're close to A?
Because otherwise the difference is too big.
That gap is too big otherwise. Does that make sense? So as we get closer and closer to A, we get this tiny, tiny little gap, and we end up actually getting a pretty reasonable guess. And certainly dealing with a line is a lot nicer than dealing with a curve. And so that's how we're going to use this linearization. We're going to say, as long as we're close to A, let's just use it as a guess, as a reasonable approximation. Okay? So that's what this whole yellow box says. And then I have just, this slide is just kind of, so I can put this on the wall eventually. So it's just saying the same thing. So let's try this for this function here, x squared plus 1. Okay? And if you notice, the question is find the linearization of f of x equals x squared plus 1 at x equals 1. So at this red point, if I'm asking you to find a linearization, I'm asking you to do what? I heard somebody say it. Yeah, find the tangent line. Exactly. So, well, we know that the linearization, we need the value at A, right? Our linearization is the value at A plus the derivative at A times x minus the value at A. So A is what point on this graph? What is my A for this graph? Yeah, exactly, 1. So what is the value at 1 plus the derivative at 1 times x minus 1? So what is the value of my function at 1? what is the derivative? So now we've got to do a little bit of work here. If this is the function, what is the derivative of this function? 2x. So what is the value of my derivative at x equals 1? Okay, so I have a slope of 2. So at this red point, I'm at 1 comma 2. Right? I have a value of 2. I happen to have a slope of 2 as well. So there's my linearization at x equals 1. If I wanted you to give me the linearization at x equals negative 1, would it be the same or different? Would I get the same answer here? Okay, I see some people shaking their head no. Why wouldn't I get the same answer here? Yeah, exactly. Okay, I would have a different slope. I certainly have a different point here. So when I put in this point for x, I would put in a different number. I happen to have the same y because of the symmetry. That was coincidental. Okay, so this linearization is just for x equals, just for this location. Remember, another term for linearization, I mean, you said it a little earlier, right? It's the equation of the tangent line. And so we have one equation for this, and we would have a different equation for that. Okay, so I should be able to go ahead and type in my linearization expression. So this is, for me at least, this is actually a live graph. So I'm going to go ahead and put in 2 plus 2 times the quantity x minus 1. And there is the linearization. So there is that tangent line. Okay? So far, so good. So we've linearized that function. Okay, it's not tremendously impressive. It's only good to approximate the value of the function near that value 1. But, you know, it's an okay approximation as long as we're going to stay close to 1. So we're going to try to stay close to 1. And we're going to come up with a couple of values. It would be nice if I could simplify this a little bit, but I don't have to. Here's my linearization, 2 plus 2 times the quantity x minus 1. Okay? And what I'm going to have you do is I'm going to have you complete this table. So I'm going to have you take a second to complete. I want to know what the value of the original function is at those different values. And if you look at your graph here, we see that we have a yellow dot, a green dot, and a blue dot. And that coordinates with the yellow, green, and blue in the table. The black in the table, I couldn't draw a black dot. It just kind of blended in with the red dot. Okay? But I'm going to give you about 3 minutes or so to come up with these values, and then I'll assign a table to report out the values on this 2, 3, 4, 5 on this graph. So why don't we do this? These two tables, I'm going to give you yellow. Okay, so between you 4 people, come up with the yellow values. That'll work. I'm going to have you 2 do the green values. Okay. I have your 2 do green values. And thank you. I'm actually going to have that table do the blue values as well. And just coordinate. I'm going to have you do the black values, and I'll do the red values. Okay? And then once you have your answers, go ahead and send somebody up there to get the answers up on So give me like 4 decimal places, even if the couple of the locations are zeros. And then when you have the 2 answers for your group, go ahead and put them up there.
Oh yeah, no.
Because what we want an equation for a line that's going to linearize this function. Okay? And so, so what we're saying is we're going to draw this tangent line. We're going to draw this tangent line there. And so we have an equation that can't meet x and y. Okay. And so, so this basically.
Yeah,
So basically what we have is and then final equation for this line is
I don't know. I think I was 6.
and so we write that equation to minus over x minus
Isn't it?
this derivative and
So you'll have to do this, isn't
Ryan has to go.
That's A, exactly. Okay. Good deal. We got one group up there. And short straw, touch the nose last. Fill it up and views. Touch the neighbor's nose last.
It's supposed to be 2 for both of them.
That's okay. And I gave you the low spot too, right? Which makes it
Yeah, I know, I tried. Oh, yeah.
Awesome. Okay, I believe that means 2.000, and this also means 2.000. Okay. Okay, so if we look at the function and we look at the linearization, which is nothing more than the approximation, we see that we have a difference of 0.04 here. We've got a difference of 0.01. We've got a difference of 0.002. We've got a difference of 0.00002. And we've got a difference of nothing. Okay? So as we get closer to that center value, okay, that value where we are tangent, we see that gap disappear. Okay? And it's reasonable. I mean, even if we were within, here's 1.1, here's 0.9, that would be kind of centering 1.0. We're still within 1/100th. 1/100th as a percent is 1%, so it's not bad. Try. The yellow says 2.4400, and then 2.4000. Should have picked a different color. Let me just go orange on you there. A little better. Okay. So we see that gap disappear. So that's all about, that's exactly what an approximation is about. Is as we stay close to x equals 1, we're going to have really, really close values, whether we use the line or the actual curve to calculate our value. That's what an approximation is. Okay, so for tonight's WebAssign, when I'm asking you to linearize, I'm just asking you to get that equation. Okay, get that equation for that tangent line. Now, what can we do with this? We can actually predict roots to equations. Okay, so well, we can actually, there's a process now where we can actually get the roots without doing any fancy factoring. So as you're finishing that up, think about what a root might be to an equation. What does that mean? So we are looking at that next page, and that we're looking at roots for the equation. Okay? Okay. So okay, linearizing can also be used to find roots of functions. So just a quick review. We have a function and we say it has a root. What does that mean? What does a root mean? What does it mean graphically? Roots are what? So, well, if I have some sort of polynomial function, let's say I have a function that looks like this.
Dictates the curve.
Here's my f of x. How many real roots does that function have?
3.
Where are they, and how do you?
1 y equals 0.
When y equals 0 on the x-axis, however you want to say that. I won't even talk about that one. We could assume that, it probably goes on forever and it's also a root. But in fact, let's do that. Let's assume that this goes on forever so that we know we definitely have another root here. So we have 4 roots. Where they cross the x-axis. And somebody said something about y that I thought was important.
Y equals 0.
The y coordinate equals 0. So if I would write this in coordinate form, I would say I have some value x, but the y value is 0. And that x must be a root then. Okay? So we can use linearization as a means to guess that root. Okay? Without having to do anything fancy with factoring. We can just literally take a look at the picture and say, well, this value is close to 4, so I'm going to guess 4 and go through this process. Okay? So if we take a look at this and say, well, I'm going to guess a first root, and that first root, if it's a root, means it's going to have a y value of 0, then I'm really kind of saying I'm going to guess this point as my first point. I'm going to guess that it's a root. Is that point a root?
No.
Really isn't. Well, it's my guess, which means what I think is I think this function is actually way down here and crossing here. And that's okay, because this is just going to be a guess. And that guess is going to be self-correcting, which is really nice in this process. Okay, so my guess is going to be x sub n. And so that value, then the function value is going to be f of x sub n. Okay, and that's going to be my guess. And I'm going to guess it's a root. So if I'm going to guess it's a root, then I'm going to guess then I'm assuming its y value is what? 0. Exactly. So in terms of this is, and again, I mentioned a little earlier, it's the notation that's kind of the clunky part. In terms of putting this guess into here, it really kind of looks like this. I've got this guess, it's x comma 0, it's a root. So I'm going to put that guess in for this equation. And I know this equation goes through this point, and I know that this equation has this point of tangency, so it has this derivative, it's written somewhere, it has a slope that is this derivative. So I can actually put that in for the slope of the m, slope value m. So this equation then, I kind of wrote over it down here, but this equation then looks like putting in this root. So this root is then a value of 0 and an x value of x. Okay, the y1 and the x1 are this point here. So what are these points? My y1 is my function at location n, and my x1 is the value of the function at my first guess n. And then my slope is the derivative. Okay? So, and again, the notation is what's clunky here. But really what we're looking at is I have a location x. I can find the value of my function and my derivative there. And from that, I'm going to find a new n. Okay? So if I solve this for x, what does that look like? And this is where kind of the tough, the notation, looking at the notation kind of makes it tougher than I think if the notation weren't so clunky. So we have this, we have a function, and we have our derivative, and we have our value. So how do I solve for x? So I'm going to have to solve for this variable, which means this has to go to the other side. How does that happen?
Divide. And then add.
Right. Then I'm left with that. So I end up having this. In other words, the value of the function over the value of the derivative. And then that. And then as I solve for x, I get something that looks like, so solving for x means this goes to the other side. So we end up having value of the function over the derivative with a minus sign in front of it, and then plus x sub n. Okay, and this is something that's called Newton's method. So Newton's method is set up specifically with a 0 in the y location, because we're guessing, our Newton's method is used for guessing zeros, or guessing roots. And then as we solve to guess for our roots, we have what we call this iterative process. In other words, we take our guess, we find the value of our function and our derivative, we put that into an equation, and from that we get a new value for x, and then we start the process all over again. So if you look at this equation, it looks just like the one up here with the terms reversed. You get rid of that line, that curve now. It looks just like that with the terms reversed. Looks like that. And so I'm going to go ahead and put those terms in the order that you see them up there. So we have our value for x is our old value minus our function over our derivative. And so we can use this then to start finding zeros in an iterative method. So we're going to try this on one of the examples. So any questions about the notation before we try this on a physical example? We're looking at getting, just like the linearization, we're looking at getting 3 pieces of information: an x value, a y value, and a derivative value. And using them in linearization, we were using those in a slope point form. And Newton's method, we're using them in a slope point form rearranged to solve for x.
Wait, why did it change from plus xn to xn minus?
I just, there's a minus sign here.
Oh.
All
Okay.
I did was take these 2 terms and do this, because that's the way you typically see it written. Okay, so let's look at then, this card is just kind of repeating what I said, and repeating the equation for Newton's method. But I do want to talk about something on this card. The one caveat to this, it says this method is valid as long as the derivative is not equal to 0. What happens if the derivative is equal to 0?
There's no slope.
Yeah, which means what for our tangent line?
It's equal to 0.
It's this, right? The tangent line is horizontal. And so think about hitting a function. If we have a function and we're trying to linearize a function, and we hit this point where the derivative is 0, then does that ever cross the x-axis? It never crosses this x-axis, which means it never gets a value of y equals 0, so we can never consider it to be a root. So the derivative, if the derivative is 0, it doesn't mean we can't use this, it just means we have to pick another starting point. Okay? And so also, if you notice, the derivative being equal to 0 makes that fraction undefined. So you literally can't calculate anything. Okay, and again, that doesn't mean we throw out the method, it just means we throw out the guess and pick something else. Okay. So let's take a look at this value, this function here. This function is natural log of x minus 1. And so we need to know 3 things. The first thing is we need to have a first guess. Okay? And I'm going to have your first guess be 3. Then we need to know the value of the function at 3. So what happens when we put 3 into this expression? What do we get? What's a natural log of 3 minus 1? So grab a calculator, give me a decimal We know we're doing approximations, and we know we're doing a process where we're going to see little itty bitty changes. So give me 4 or 5 decimal places. What do you get for a decimal there? Anybody got that decimal for me yet?
You get
0.09861. Awesome. Okay, now we need the derivative. So if that's my function, what's my derivative? 1 over x, exactly. And then the derivative of -1 is 0. So what is my derivative at 3? 1/3, or 0.33. So we're going to put that all together. We've got a guess of 3. We've got a function value of 0.09861. We've got a derivative value of 0.3333. So we're going to go ahead and calculate that whole thing. So we're going to go ahead and calculate 3 minus 0.09861 divided by divided by 0.333. So what do we have as our new x guess? How much? Well, what's 3 minus that? You just calculated the fraction, right? Yeah. $2.7039. Okay, so we have our new guess of 2.7039. So our calculated answer becomes our new guess. So it got us a little bit closer. You know, we were at 3. Now we're at 2.7. We actually overshot our guess. So we're going to go through this process again, this iterative process again. So now our function is the natural log of 2.7039 minus 1. And how much is that? Okay, 0.006759. 0.00759. There you go. 0.00759. Okay. Yep, now we have to find the derivative. Exactly. So the derivative, Oh, minus 1.
No, it's still.
Oh, in other words, it's still that much. Even because you subtracted the 1. Yeah, you subtracted the 1. I knew the number sounded familiar. Okay. Is that what you got? Negative 0.005? Okay, that actually makes a little more sense. Negative 0.005? Okay. 5.3. Should make these boxes bigger. There you go. Okay. And then we need to find the derivative, which is 1 over 2.7039, which is how much? $3,698, and then we can find our next guess. So now we're going to take that 2.7039 and subtract this divided by that. So we're going to subtract 0.0053 over 0.3698.
We're supposed to be in degree or radians for.
Are we dealing with angle measure? Okay, so it doesn't matter. Yeah, as long as we're not using that theta button, we're good to go. So now our more recent guess is 2.718. So you notice how it came back a little bit. So if we look at that process we did, those 2 steps, this got us something that was over here. It actually jumped on the other side of the root. And then when we use that to estimate, this one got us back a little closer. And that's okay. If you might jump over the root and back again. It just means you've reversed, you're on the other side, so you've got that negative value now. And then if we went through this a third time with 2.718, we would find that we actually get an updated value that still is 2.718, and the only thing that changed is the stuff beyond the decimal point, beyond the 8. So, so we're already getting as close as 1/1000th, just in 2 steps. So you actually get you really close pretty quickly. Okay, and so we've done that. If we would do that a third time, then we would have that third approximation. So we use that linearization rearranged into Newton's method so that we can approximate these roots. And it doesn't take us too long to be able to approximate them. So questions about that? Okay, so you've got a couple of linearization questions in Web of Science tonight. I think 3 of those, finding equations of tangent lines, basically, and then 2 Newton's methods for the 4 or 5 homework. For 4-6, tomorrow, related rates has to do with implicit differentiation. So remembering things like the derivative of y squared is 2y prime. We're going to use that tomorrow. And then that leaves the last day of the week just to kind of finish everything up, finish up the 2, 5, 2, 6, 4, 5, and 4, 6. And then also getting back on finishing up stuff from the previous sections. Okay?
Yes, Father.